So far, so far. Okay. There's another question somewhere, I thought. Maybe not. Okay, keep going. Now, we've talked about using the z-axis. This is how we usually do it. We calculate the z value for our data. Again, this is our data. This is t bar. And we figure out if it's greater than our critical value of z. You can also do this by calculating the rejection region on the t-axis, back on the data axis. And you take this relationship and you invert it. I'll go over here to do that. Okay, so I have z equals x bar minus mu sigma over the square root of n. Now let me solve for my x bar, and that's just equal to mu minus z sigma over the square root of n. And this, of course, looks a lot like our confidence interval formula, which it does resemble. And this then tells us the value, the critical value, beyond which we'll have that low probability. So now I put in my 130 minus the critical value 1.96, so this would be z of alpha over 2, and 1.5 over the square root of 9. And I calculate that, and I get 130.98. And that is, of course, less than, my t-bar is greater than this number, and therefore I'm past that number. So this critical value, the edge of the rejection region in this case, is 130.98. And it's on this side, so our data is off in that rejection tail. Yeah.
Is it x bar to put a mu plus?
I'm sorry?
Is it x bar to put a mu plus c sigma over square root? Yes.
I didn't understand, I'm sorry.
In the x bar formula, is
Yeah.
it mu plus?
Oh, yeah. So remember, with the two-tail test, I have mu plus and I have mu minus. So I should actually write this as plus and minus z alpha over 2. And then this is plus and minus, but I only care about this one, and therefore I get the upper limit. If I put in a minus sign here, I'd get the reflection on the other side of the beam. Okay, so that's the idea behind all the confidence interval stuff, or hypothesis tests we've done. Now, what if I didn't know this? What if I didn't know the population standard deviation? Then I would use t instead of z. What would happen to my value for the critical statistic? So instead of z alpha over 2 is 1.96, what kind of number would I get? So if I say sigma pop is unknown, then my z goes to t. The z value is 1.96, and my t value is 2.2, try again. Oh, it is 2.306. Okay, in that case, would I reject this hypothesis? No, because my curve just got wider. With only 9, the curve is significantly wider. The tail moves out, and now my rejection region has moved outside my data. So I would have a p-value, instead of being around 4 or 5%, my p-value would now be like 6 or 7%. And so knowing that standard deviation allows you to draw a tighter curve than if you don't know it and you have to estimate it from the sample standard deviation. Yes?
In that case, we wouldn't know sigma, right? So how
Right, we'd use S squared.
so we would be given S squared.
You'd have to be, yeah, yeah.
Okay.
So you'd use S squared. Yeah. So you know the T formula is x bar minus mu s over the square root of m. So it goes right in there, yeah, in the formula. Yeah. Okay. Any other questions? Okay, let me make some room and we'll do a confidence interval. I haven't lectured at a chalkboard in about a year. You know, since I videoed all the lectures, it's like, I don't do this anymore. Okay, let me find my last sheets here. Here we go. Okay, so we're back to filling bottles. Remember the problem we had with filling bottles. And this bottling machine has, let's do n equal 20 samples, and we get a fill, and I should say a fill of 2 liter bottles, and 2.02, 1.95, 1.98, and so on. And we find that the sample standard deviation for these 20 is 0.001352. Okay, wow, isn't that amazing precision? It's 1/1000th for 2 liter bottles. Why is that not the right way to think about this? Why is the pertinent number much larger than 1 in 1,000?
It's over the square root of
I'm sorry?
n. It's over, like it's divided by the square root of n.
Correct, it's squared. Okay, this is the variance. Sample variance. So if you want to think about physical numbers, so this is like liters squared. I have no idea what a square liter is. 6-dimensional. So it would be the square root of this, so it's more like, 0.03, much larger. Okay, so then let's ask, what's the 95% confidence interval on the standard deviation? So the bottling company wants to know, what's the real range of variability here for this fancy new machine they just spent hundreds of thousands of dollars on? Okay. So, for this we use the chi-squared distribution. And again, it's going to look like this. You'll notice I'm drawing a sketch of the problem before I start. Okay? And we're going to have a confidence interval width that looks like this, and this is going to include 95% of the probability. And so I want 2.5% in this tail, and I want 2.5% in that tail. Okay, so I then need to calculate the critical values. One on this side, one on this side, so this is going to be chi-squared. Chi-squared is like t, it has 2 subscripts. If this is alpha over 2, then this would be chi-squared of alpha over 2. And then the number of degrees of freedom is n minus 1. Yeah?
Wouldn't it be 1 minus alpha over 2?
No. Good point. I'm glad you asked that. Okay. The notation in the textbook, the notation in almost every website you find looks like this. This subscript is the upper tail. Okay? If you use MATLAB, then you'll use chi2CDF, and you'll put in here the 1 minus alpha over 2 and n minus 1. This is the lower tail. So if I put in 1 minus alpha over 2, then I'll get 97.5 below this. So this is 97.5% below. And this is 97.5% below. Okay, it's this unfortunate difference between the way MATLAB calculates things. It's always a CDF. The good thing about MATLAB is Z, T, whatever, it's always the probability below the argument you give it when you use the CDF function. Here, it's the upper tail. There's actually some notation where it's the lower tail. But MATLAB is at least consistent, even if it doesn't agree with the notation of the text. Yes?
Would we use chi-squared inverse to find the value that we need to calculate the standard deviation?
You're right. This would be chi2 inverse in this case. So you give it the probability, and it gives you back the chi-squared value.
So
Thank
that's
you.
what, that expression is what we should use, or is it not what we should use?
It is. This will give you back the value that has this much probability below it. It's the lower tail. So this is how much probability is in the lower tail. This is how much probability is in the upper tail, the subscript here. Okay? Now I'll tell you why for two-sided constant intervals you don't have to worry so much. So what's this one going to be then? It's going to be chi-squared 1 minus alpha over 2, because it's going to want to have 97.5 in the upper tail. And then it's going to be n minus 1, of course, as well. Okay? Now, when you actually go to calculate the confidence interval, we use the formula n minus 1 times s squared over chi-squared 1 minus alpha over 2 n minus 1 is less than sigma squared is less than n minus 1 s squared chi squared 1 minus alpha over 2 n minus 1. Oop. Alpha over 2 n minus 1. Now, if you calculate this, and for instance you get a number like 20 here, and a number like 3 here, oops, you got the tail switched, okay? So if you do a two-sided interval, it's always easy to catch because the big number goes on the right, okay? One-sided confidence interval, you have to think. But two-sided, it checks itself when you actually write down the numbers. It's pretty obvious. Okay. So then basically we just plug in this formula with the numbers we had before. So we have 20 minus 1 times 0.001352 over this value, which is 38.852. It's less than sigma squared. It's less than 20 minus 1. 0.001352 over 8.907. Okay? And it works out to, we'll do it up here. I'll write it as this kind of an interval, 0.000782, 0.00288. And that's for the variance. So we take the square root and we get 0.0279 and 0.0537. Okay. So in a 2-liter bottle, it's the variance is somewhere between 27 milliliters and 53 milliliters. Yeah.
So the lower bound in this case is the left value, just to make sure.
Okay, let's reason this through. Let's go back here. The probability in the upper tail is alpha over 2, so this is chi sub alpha over 2 n minus 1. So this is going to be the bigger number. So we want the bigger number. Oh, you're right, I got these backwards. I apologize. See, it's easier to get backwards. Alpha over 2 here, 1 minus alpha over 2 here.
So then the lower,
The bigger number
the next line.
has to be here, and the little number has to be here, right? Because you want a bigger number on this side and a smaller number on this side, and the numerators are identical. Yeah.
And if then the problem asks us to find a lower bound, do we want to have the little value or the big value?
Okay, so when you say a lower bound, it usually means I don't care about this one, I want all 5% in this tail. Okay, then if ignore the notation. If you're just using MATLAB to look up values, what number would you put into MATLAB for a lower bound? Right, you want this much probability because it's the lower tail. So this would be chi 2 inverse the probability alpha over 2 and whatever your degrees of freedom is. For the upper bound, it would be chi 2 inverse the probability here is 1 minus alpha over 2, so this is like 97.5 because you want all that down there. And then this is k. Make sense?
So the lower bound would in fact be the smaller value for the.
Yeah. This increases, right? This is 0 down here, and this goes up to, infinity, positive infinity here. So the numbers get bigger as you go along that axis.
And then in your last line where you were plugging in the values for the chi-squared,
Yep.
would that now be flipped, or was that correct?
No. Big numbers here, right?
That's the smaller number.
38.8.
Yeah, okay, but then the standard deviation on that side is smaller than the
Yeah.
other side. Okay.
Yeah.
Okay.
Less than.
So that in
It
the
could be less than or
last
equal to, it doesn't
denominator
matter if it continues the deviation.
Okay. Thanks.
Okay? Yeah.
So you have written down there, the lower bound, chi squared 1 minus alpha over 2, n minus 1, but then we're saying that for chi to inverse, use alpha over 2.
Yeah, that's the point. I'm going to find a textbook that doesn't do this. But then you'll get confused when you look at any other textbook. I don't know, there's no hope. Yeah, it's confusing. The thing to think about, I think, from your point of view, the exam, solving problems, is MATLAB gives you the lower tail. Draw the picture, you know what the lower tail is. Here, it's just alpha over 2. Here, it's 1 minus alpha over 2, because you want all this probability on the left side of that number.
Okay, so the reason why you put 1 minus alpha over 2 down there is because that's what we would use on that side?
No, because that's the way our book does it.
Okay.
Our book does upper tails. Our book says, this subscript tells me how much probability is above
Going
that value.
rather than that.
Our book is backwards from MATLAB, as are most statistics books. That's the notation that's used. I didn't get a vote. I wouldn't do it this way, but
Okay.
you'll figure it out. It's not that hard. Okay, that's all I had. And at this point, I'm happy to answer questions either here or individually. Yes?
One last question. For these kind of problems, here you gave us s squared, right?
Yes.
Okay. So, and if we didn't have x squared, we wouldn't be able to solve this problem.
S squared.
S squared.
Yeah, that is correct. Yeah.
Well, if you gave us like all 20 of them, I guess we wouldn't be.
You calculate.
Okay.
Yep. I don't know, I seem like that kind of mean guy who make you type in 20 numbers, so you get typos, and then you get a wrong answer. Yeah.
I was looking on Canvas and the slides with answers didn't seem to be posted. Will they be posted?
I thought I was up to date on those. Let me check. Something that I've noticed happens is the file is in the files, so there's a files tab which has got a bunch of subfolders. There's one called class. So I upload those, and then I put a link in the module, so you can just look in the module. That link to the module breaks once in a while.
Okay, let me go with
So yeah, I can fix that instantly if you tell me about that. Yeah. Did other people have that problem? Yeah, you can look at the files, they should all be there. Again, the version we're using class without the answers is the end of the file name is inclass.pdf. And if it doesn't say inclass.pdf, it's got the answers. More statistics related questions? Nope.
So there's slides that are entitled lecture 12, but we're not going to cover
No.
any of that.
No, it's only the stuff that's covered on the problem sets. And we didn't do the last class, obviously the problem set was due, so it wasn't covered.
So going up to the one that says class 11, so all the material for class 11. Okay,
Sounds right.
cool.
Although I think I should be careful. Class 11, we talked about
Tolerance and-
confidence intervals with variance. That's on the problem set.
Okay.
But prediction and tolerance intervals, we covered in that class. I didn't put on the problem set.
Okay.
Because I didn't know if we'd get to it in time. Yeah.
I have a question about null.
Sure.
So in the example, we were trying to determine whether the company's claims were correct, but then our null was that they were correct.
Yes. So the way I think about it, the way I think it's useful to think about it is, what do I believe unless there's strong evidence? So there's a new drug. I will believe it's no better than the old drug unless there's strong evidence. The manufacturer told me this is true. You know, I'm doing quality control. I'm buying something and I want to make sure the parts are inside tolerance. And I measure them and, I do a hypothesis test. I want to believe my supplier shipped me good parts unless I can really go back to him and yell at him and tell him this is garbage. Look, I've got a hypothesis test with a 2% p-value.
So in that case, the null would be that all the parts are okay.
Yes, whatever specification they told you this is the tolerance, you believe that until you have strong evidence to the contrary. Okay, I'll stick around. Let's turn this off.